Right, so starting from today, we have a short topic on what's known as intermolecular forces, okay, and all the things that are associated with intermolecular forces. Now, intermolecular forces are important because it's intermolecular forces that control what the bulk properties of a molecule are, so whether or not they're a solid, or they're a liquid, or they happen to be a gas. And so we're going to look a little bit closer at that. So to start with, we're going to look at periodicity. And I believe Dave had a short look at this at some point. But basically, periodicity is how properties trend as we go along and go down the periodic table. And they're actually really important because they're the most useful organizing principle in chemistry. Okay? The whole periodic table was developed around the idea of periodicity and how elements can fit into different groups and on different rows, depending on their properties and how similar they are. The good thing about these trends is they can be explained in terms of electron configurations, okay, which you guys have seen before, and nuclear charge, which again you guys have seen that before. So the first one that we look at is the idea of atomic radius, okay? So we're going to start simple with the smallest part and we're going to move up, okay? So the atomic radius is the size of an atom, okay? And we define it as how far from the nucleus the valence electrons are. Okay, so you guys should be familiar with where the valence electrons are, the most outside electronic shell, yep. And to be quite honest, to try and determine that for a single atom is really hard, okay? Orbitals are funny shapes, and that makes their edges quite fuzzy, and you can't actually see where they end. So the best way to sort of determine atomic radius is to look at atoms in a bond. So what we do is we look at two atoms which have formed a bond, yep, and what we determine is half the bond length, so half the distance between the nuclei of the two atoms. So if we look at hydrogen, for example, okay, what we have here, two hydrogen atoms, the little blue dots denote the nucleus, and the distance in between is 2 times the radius. So if we halve that distance, we can get an idea of what the atomic radius is. And so for hydrogen, what we find is that it should be about 37 picometers, okay? And if you're interested, that's 3.7 times 10 to the negative 11 meters, okay? So it is quite small. But it's to be expected because hydrogen is the smallest atom on the periodic table. So of course we're looking at trends across the periodic table. So what we have here is atomic radius against atomic number. So starting from right at the top of the periodic table and moving down to element 19, chlorine here, okay? And what we find is that as we move along a row on the periodic table, right, atomic radius tends to decrease. As you can see here, moving from lithium through to fluorine. So that's the top row of the periodic table, well, second row of the periodic table, okay? And as we move down a group, so say group 1, as you move from hydrogen to lithium to sodium, okay, what you find is that the atomic radius gets bigger. Now there are reasons for this, which we're going to look at. You guys copying that down, or can I move forward? I'll ask now. No? All right, so I'll move on. Okay, now the reason being is the increasing number of protons in the nucleus as we go across each row. All right, now this is for, as we go across the row, those atomic radii are getting smaller. And the idea is that the more protons you have in the nucleus, then the nuclear charge is greater, and that's going to pull the electrons closer to the nucleus. All right, so that makes sense? All right, so we have, for example, lithium, right, with 3 protons, and that's going to pull in its electrons. And then if you compare that to the other end, where we look at oxygen with its 6 valence electrons and 8 protons, the effective nuclear charge is going to pull those electrons in tighter to the nucleus and, in fact, make the atomic radii smaller. Yep. All right, and so if we look at the other trend that we saw as we go down groups, right, so the atomic radius increases, and this is because the valence electrons are in further and further orbitals as we go out. Okay, so as you move down group 1, of course you're moving from 1s to 2s to 3s. Each one is considerably bigger as we move down. And so, for example, here we have lithium, where you've got your 1s orbital and your 2s orbital. And if we compare that to sodium, which is the next one down, you have the 3s orbital, which is a lot further out, and therefore the atomic radius is a lot bigger. Also, as you get further away from the nucleus, okay, the attractive pull on the electrons becomes shielded by those electrons that are in the inner orbitals. Yeah? So if you're an electron in the 3s orbital, then you have electrons in the 1s and the 2s and the 2p that are in your way between you and the nucleus, and so therefore the way the charge is felt is lessened by having those other electrons in the way. And this is what we refer to as the effective nuclear charge. So that's how you describe the positive charge that the valence electrons can actually feel. And so as you get further from the nucleus and you get more electrons in the way, the effective nuclear charge becomes lesser, the electrons are less tightly held, and the atom gets a lot bigger. What we find is that trends in ionic radius, okay, tend to be quite similar, except for the fact that when it comes to ions, we can be dealing with either a cation, a positively charged ion, or we can be dealing with an anion, a negatively charged ion. And so properties tend to change a bit depending on charge. So when you remove an electron, okay, from the atom you form the cation, the positive ion, and the resulting ion is smaller than the starting atom, which would make sense, right? Because you're moving an electron, removing an electron. And then when you add an electron, okay, to get the negative anion, what you get is a larger ion than the starting atom, okay? Which again makes sense because you're adding to it. So, lithium atom, all right, which should look familiar, 1s orbital, 2s orbital. If we then look at the cation, all right, so we're going to remove that valence electron, and we've shifted now into the 1s orbital, and so the cation is a lot smaller than the atom. You can also explain this in terms of the effective nuclear charge felt. Okay, so here we have 3 electrons that will be feeling the effect of the nucleus, and so we have fairly light effective nuclear charge when compared to here where we only have 2 electrons feeling that effective charge. Yeah? So the more electrons you have, remember, the smaller your effective nuclear charge. And then if we look at the other half of the equation, so this time we're going to look at oxygen, which has 8 protons, 8 electrons, 6 of those electrons in the valence shell, okay? And then we take 2 of those electrons away. No, we add 2 more actually, sorry. If we add 2 electrons to form the anion, so now we have O2 minus, 8 protons and 10 electrons, okay? Well, you'll note here, there's pictured, the ionic radius gets bigger. Now the reason for that is twofold, okay? One is the effective nuclear charge, like we've been talking. So if we add 2 extra electrons, this acts to lessen the effective nuclear charge, and of course the electrons will spread out. The other reason is what's called electron-electron repulsion, okay? So if you remember, electrons are all negative charges, and they're going to repel each other if they get too close. And so if you pack 2 more electrons into that orbital shell, they're going to spread out further to lessen those repulsion interactions. Right? And this effectively increases the ionic radius. So if we have a look at some of the trends, so we see here, okay, and here's a lithium example. All right. In grey you have the relative size of the atom, and in pink you have the cationic size. So what you can see is for lithium we have 0.68 picometers compared to 1.34 picometers. So as you take that electron away, there is actually quite a large difference in size. And you can see that as you move across in terms of cations, right, just like atomic size, your cationic size gets smaller. And as you move down the group, okay, your cationic size gets bigger. If we look at the anions, and we can look at the sulfur example here, so we have S and S2. Right, the atom size is 1.02 picometers, and the anionic size is 1.84 picometers. And again, as you move down the periodic table, okay, the anionic size scales with atomic radii. Yep. Cool? Okay. All right. So we also need to note that in cases where we have two different cations of the same element, so for example, if you have iron 2 plus and iron 3 plus, okay, so they're both iron, but they're two different cations. Right? The size decreases as the charge increases. Now this will make sense because as we take electrons away, we're increasing the effective nuclear charge. And so we should end up with smaller ions. And so for example, if we look at germanium and tin, okay, here would be the atomic size in a covalent bond. And then if we look at the 2 plus ion, for germanium we have 0.87. You move out to the 4 plus ion, and you know it gets smaller to 0.67 picometers. And the same sort of idea for tin. As we increase the charge, the size of the ion gets smaller. All right. So the next thing that we want to look at is electronegativity. Electronegativity is a measure of how much an atom will attract electrons to itself when it's involved in a bond. Okay? And it's a very important concept for explaining chemical behavior in a lot of compounds. And it tends to be in the majority of compounds. And it's going to be an idea that we're going to look at in depth as we move along. So you guys should hopefully be happy with the idea that as we move across the periodic table from hydrogen across to fluorine and so forth, that the electronegativity increases. So basically fluorine is the most electronegative element, and as you move away from fluorine, it gets less and less electronegative. So as you move down, your electronegativities decrease. As you move across, your electronegativities increase. Yeah? Cool. It's the same sort of periodic trend that we've been looking at with the last two examples. So if a bond contains two atoms with different electronegativities, okay, then the electrons in that bond tend to spend more time at the end that is more electronegative. Okay? So if you remember, your electrons move around the nuclei. If you're in a covalent bond, then those electrons are moving around the two nuclei. And if you have one that's more electronegative, then the time the electron spends moving around that bond is spent more at the electronegative end. So if we take, for example, oxygen, which has an electronegativity of 3.44. I'm not sure which scale they're using because there's two of them. But they both pretty much tell you the same thing. And if you take hydrogen, which has an electronegativity of 2.2, so we have an OH bond, which you guys should be fairly familiar with now. What happens is that the electrons will tend to spend more time at the oxygen end than they will at the hydrogen end, because the oxygen is more electronegative. And so therefore what you get is what's called a partial negative charge on this oxygen, okay, which is denoted delta negative. Yeah? And in effect what you have on the other side is deshielding of the hydrogen nucleus, and you end up with a delta positive charge, a partial positive charge on that end. And in effect what you form is what's called a polar bond. So this brings us on to the main part of what we're going to talk about. Oh, actually, yeah, I should explain that. Right. The way we describe this type of phenomenon is as a dipole, okay? So two poles. So one pole and two poles, positive one, negative one. And the way we denote a dipole is by having an arrow which points towards the more negative end. So this is pointing towards the end where the electrons spend most of their time, and you put a cross at the other end to denote that this end is the positive end. Yep. Cool? All right. So, all right, intermolecular forces. Okay? So, molecules will interact with each other in a variety of ways. Now, the most common analogy used for this is thinking about children on a playground. Okay? If you have a whole bunch of children on a playground, right, and you just look at them, then they look like a seething mass of kids playing, yeah? But in fact, they're all interacting with each other in certain ways, and you get certain groups formed and all the rest of it. Intermolecular forces is about the same way. Okay? You have a whole heap of molecules that are interacting with each other in some way, okay? And on the outside, they just look like a mass of something, all right? Whether it's solid, this thing, okay, or it's a gas, or it's a liquid. We won't go into plasmas, okay? So technically, there are 4 states of matter. We only worry about 3 of them, okay? Solid, liquid, and gas. We don't worry about plasmas, okay? Because plasmas are new, and we don't know enough about them yet. But typically, what we find is there are 3 general types of intermolecular forces. The first one is what's called dispersion forces, or London forces. The second is dipole-induced dipole interactions. And the last is dipole-dipole interactions. And we're going to look at those in a bit more depth. Okay, so the first one to look at. Ooh. Yeah, all right. So in all cases, these interactions are electrostatic. Okay, so we're looking at differences in charge. Okay, this is very important. Okay, that's all based around the attraction between positive and negative charges, and repulsions as well. Those tend to be important too. All right. So the first one, which are part of the London dispersion forces, these are called van der Waals interactions. So this type of intermolecular interaction is present in all molecules, okay? And it's fairly weak interaction. And it arises because electrons are moving around the nucleus all the time, okay? So even in molecules where you've got a number of nuclei, all your electrons are moving around the bonds and around the nuclei. So we need to sort of, take into account the fact that our electrons are moving all the time. And then what we're going to do is we're going to stop and take a snapshot in one instant. Okay? Now, if we stop at any one time, what we may see is that all the electrons are on either one side of the nuclei or the other. So there's the probability that they are going to be on one side rather than the other. Yes? It is a London force, yeah. Okay, so if we put some electrons on the right-hand side of our atom, then there are on the left-hand side, and then what we get effectively is a dipole on our atom. Okay, so if the majority of the electrons are on this side of the atom, then that means the nucleus on this side is deshielded. Okay, and so effectively on this side you have a positive charge, on this side you'll have a negative charge. Okay. Now what that's going to do, if we have another argon atom that's in close proximity, it's going to effectively cause an instantaneous dipole on that atom. Okay? So one atom is going to affect the other one. And so what you have is a whole bunch of instantaneous dipoles occurring, and that causes the atoms to attract to each other. Yeah? Cool. Okay. So like I said, this type of interaction is very weak, all right? And the strength of the interaction depends on the size of the molecule. So if we think about it, the larger the molecule is, then the more electrons it's likely to have, yeah? And so if you've got more electrons, then you can stack more electrons onto one side of your molecule, and this is going to make the electrostatic interaction all that more stronger, yeah? All that much greater. And so, for example, we can look at the boiling points of the noble gases. So the noble gases are everything that's in group 18 on the periodic table, helium right through to xenon. And what you notice is that as you go down that group, the boiling points of these gases gets bigger. Okay? So helium has a boiling point of minus 269, getting very, very close to absolute zero. Okay? And as we move down, right, xenon has a boiling point of minus 108. So as they get bigger and they have more electrons, then the stronger those van der Waals interactions become. All right, so the next one on the list are dipole-induced dipole interactions. Now, these interactions are found between two different molecules usually, okay? So for this example, we're going to consider water, okay, and oxygen. Now, if you remember, water is H2O, so you have two H bonds there. So basically, you've got two polar bonds, yeah? So what you have on water is, in fact, two dipoles, yeah? You have this dipole here and this dipole here. And so the oxygen has most of the negative charge, the hydrogens have partial positives. Oxygen is a bond between two O atoms, okay? And so therefore there's no difference in electronegativity. So that's not going to have a dipole. But if you get it close to, say, a water molecule, which has a polar bond and a dipole, what you're going to do is you're going to induce a dipole on the oxygen atom. And so we have that in blue. Okay? So what's happening is the positive charge on the hydrogen is inducing a negative charge on the oxygen in the oxygen molecule, and so therefore the electrons are pulling this way, and you end up with a partial positive charge on the other oxygen. Now, these types of interactions are a little bit stronger than van der Waals interactions, but not by much.